welcome you all. I am Ms.G.Thiripurasundari, lecturer, PG Department of Mathematics, Seethalakshmi Ramaswami College, Tiruchirappalli. In this section, I am going to discuss on the basic concepts on limit points. The content, what are the contents we are going to see are neighborhood, open set, closed set, limit point, and illustrations. Before going to the original definition of neighborhood, I just want to recall the concepts of intervals. If we choose any two real numbers a and b with the relation that a less than b, there exists infinite number of real numbers between a and b. This can be represented in the form of a less than x less than b, and also can be represented in the form of open interval a comma b. In this open interval, the endpoints a and b are not included. If we include the endpoints a and b, then it becomes the closed intervals a comma b. Now I give the definition of neighborhood. A set n subset of R is said to be the neighborhood of a point P belongs to R if there exists an epsilon greater than 0 such that an open interval P minus epsilon comma P plus epsilon contained in A. The alternative definition is a set n subset of R is said to be the neighborhood of a point P belongs to R if there exists an open interval A comma B containing the point P and it should be completely contained in A. The illustrations. The open interval a comma b is the neighborhood of each of its points. The set of all real numbers R is also the neighborhood of each of its points. The closed interval a comma b is the neighborhood of each of the points of the open interval a comma b, but it is not the neighborhood of its endpoints a and b. Because if we take the neighborhood for the endpoints, it is not completely contained in this closed interval a comma b. The last example is the set of integers is not the neighborhood of any of its points. Next, we move to the definition of interior point. If n is a neighborhood of a point P, then we can say that P is an interior point of A. The example is, if we consider an open interval a comma b is a neighborhood of each of its points, then the collection of all points in this open interval a comma b is called as the interior point of the corresponding set. Then comes the definition of open set. A set G subset of R is said to be an open set if it is the neighborhood of each of its points. Otherwise, a set G subset of R is said to be open if for each point P belongs to G, there exists an epsilon greater than 0 such that the open interval P minus epsilon comma P plus epsilon should completely contain in G. Their examples are every open interval a comma b is an open set. The interval closed A open B is not an open set because it is not the neighborhood of the endpoint A. Every singleton set is not an open set. These are the basic theorems in open set. The union of arbitrary family of open sets is open. The intersection of two open sets is open. In the remark, we are going to justify that the intersection of arbitrary family of open sets may fail to be open. To prove this condition, I am going to take an example. Let us take a collection of open intervals, that is Gn is equal to open interval minus 1 by n comma 1 by n, where n takes the value capital N, that is set of all natural numbers. Then small n takes the value 1, 2, 3, etc. up to infinity. If we put n is equal to 1, 2, 3, we get the sets G1, G2, etc. The set G1 is equal to open interval minus 1 comma 1. G2 is equal to open interval minus 1 by 2 comma 1 by 2. G3 is minus 1 by 3, open interval minus 1 by 3 comma 1 by 3. Proceeding in this manner, we get Gn is equal to open interval minus 1 by n comma 1 by n. Then now we put an arbitrary intersection of these open intervals. That is intersection of Gn is equal to open interval minus 1 comma 1, intersection with open interval minus 1 by 2 comma 1 by 2, etc. So intersection of open interval minus 1 by n comma 1 by n, intersection, etc. By taking this intersection of these open intervals, we finally get a single point, that is 0. That is, we get a singleton 0. Clearly, we can say that this set is not an open set because we already said that every singleton set is not an open set. Next comes the definition of closed set. This closed set is just a complement of open set. A set F subset of R is said to be closed if its complement is open. Their examples is every closed interval a comma b is a closed set. The open interval a comma b is not closed because its complement is not open. These are the basic theorems in closed sets. The intersection of arbitrary family of closed sets is closed. The union of two closed sets is closed. In the remark, we are going to justify that the union of arbitrary family of closed sets may fail to be closed. To prove this condition, I'm going to consider a collection of closed intervals, that is Fn is equal to closed interval minus 1 by n comma 2, where small n takes the value belongs to capital N, that is set of all natural numbers. By putting n is equal to 1 to 3, we get the intervals, closed intervals as F1, F2, F3, etc. The set, that is the interval F1 is equal to closed interval minus 1 comma 2, F2 is equal to closed interval minus 1 by 2 comma 2, F3 is equal to closed interval minus 1 by 3 comma 2, etc. Proceeding in this manner, we get Fn is equal to closed interval minus 1 by n comma 2. Then put the arbitrary union of these closed sets. By taking the arbitrary union of this collection of closed sets, we finally get the open 0 and closed 2. That is, we get an interval of the form open 0 and closed 2. Clearly, we can say that this set is not a closed set because its complement is not an open set. Therefore, the arbitrary union of closed sets may fail to be closed. Next comes the definition of limit point. It is a very important concept in real analysis. A point P belongs to R is said to be a limit point, or we can call it as an accumulation point of a set S subset of R if every neighborhood of P should contain a point of S differ from P. The alternative definition says that a point P belongs to R is said to be a limit point or an accumulation point of a set S subset of R if for every given epsilon greater than 0, the open interval P minus epsilon, P plus epsilon should contain a point of S other than P. The derived set. The set of all limit points of a set S subset of R is called as the derived set of S, and it is denoted by S dash. Illustration: the closed interval A comma B is the derived set of the open interval A comma B, since all the points in the closed interval A comma B is a limit point of the open interval A comma B. Illustration: every real number is a limit point of set of all rational numbers. To prove this, choose a point P, be any real number, and epsilon greater than 0 be given. Then the open interval P minus epsilon, P plus epsilon contains infinitely many rational numbers, and consequently it contains at least one point of Q other than P. Hence, we can say that P is a limit point of Q. Therefore, the derived set of Q is R. The second example is every point of closed interval 0, 1 is a limit point of an open interval 0, 1. In order to prove this, choose a point P in the closed interval 0, 1 and choose epsilon greater than 0. Then the neighborhood P minus epsilon, P plus epsilon in taking intersection with the open set 0, 1 again gives a new open interval C, D with condition that C is equal to maximum of P minus epsilon, 0 and D is equal to minimum of P plus epsilon, 1. This interval C, D contains infinitely many points of the open interval 0, 1 and hence P should be a limit point of the closed interval 0, 1. The third example is the set of all integers, that is Z, has no limit point. In order to prove this, first we are going to take the collection of integers. Now select P be any real number. We have to prove that P is not a limit point to the set Z. That is, every neighborhood of P does not contain the points of Z other than P. In order to prove this, there arises two cases because we have chosen P to be any real number. That is, the real number can either be an integer or it may not be an integer. In case 1, we are going to take that P to be an integer. Choose a point epsilon is equal to 1 by 2. Then the neighborhood of P is of the form open interval P minus 1 by 2, P plus 1 by 2. This open interval P minus 1 by 2, P plus 1 by 2 clearly contains the point P and no other points of Z. So that the point, this neighborhood contains only one point of Z, that is P. Therefore, P cannot be a limit point to the set of all integers Z. In case 2, the chosen point P be any real number but it is not an integer. Then choose some other integer J with the condition that J less than P less than J plus 1. then it clearly gives that it is a neighborhood for P. That is, open interval j comma j plus 1 is now become the neighborhood of the point P. In this neighborhood is also, that is, j comma j plus 1 contains only one point P and no other points of Z. And consequently, P cannot be the limit point of Z. Hence, in this case also, P is not a limit point. From both the cases, we can say that P cannot be the limit point to the set of all integers Z. Therefore, the derived set of Z is clearly an empty set. I hope from this video, you can able to get an idea about limit points.